Can you see it now?
Yes.
Right. Anyway, that's all right because I explained the background, and this is the first slide. Three-angle representation. So I think everybody understand in three-dimensional space when you have three axes x, y, z, right? If you want to represent your orientation, you need to have three angles, right? How much you rotate around x-axis, followed by how much you rotate around y-axis, followed by how much you rotate around your z-axis. Okay. Now, this is what's called three-angle representation. This is one way of representing your orientation. So when you explain it to someone else, okay, I rotate around x-axis 45 degrees, and then I rotate around y-axis 45 degrees, and then I rotate around z-axis some 30 degrees. Others can understand your orientation. Okay. So, but there are two ways to do that. You can understand if you rotate, let's say you have two coordinate frames here, right? You can see A and B, right? They are coincident here. Blue is on top of A, right? There is no orientation between these two frames, right? And after that, you rotate around x-axis, right, by a certain angle, around x-axis by a certain angle. That you can understand, okay? You did this for your homework also. So after the rotation, YB gets a different label, YB dash, let's say. Okay, so this dash represent the new direction of y-axis of B. Earlier it was horizontal alongside with the y of A, okay? So when you come over here up to this state, and before you can exercise your second rotation, right, which is around, say, y-axis, there are two disoriented y-axis. One is the original y-axis of the stationary frame, which is horizontal frame, right, horizontal axis rather, and also the new y-axis, new position of frame B. So after the first rotation, the two y-axes are disoriented. So therefore, if you want to rotate around y-axis, you have to tell me which axis that you want to rotate the second angle around, right? Whether it is the blue y-axis or red y-axis. It's all up to you. I'm not going to tell you which one is right, which one is wrong. There's nothing like that. But we need to separate them out. If you want to continue around the blue y-axis, right, it is like this. But if you want to rotate around the new red y-axis, rather, red y-axis, this is the rotation. So the second frame, which is B frame, frame B, is going to be differently oriented depending on your choice of which y-axis you're going to rotate exercise the second rotation around, right? Whether it is blue y-axis or whether it is red y-axis. So if you continue rotating around the blue axis, blue x, blue y, blue is it, we call it fixed angle rotation. Fixed angle rotation. But if you want to continue rotating around the red axis, red x, red y, and red z after this rotation, we call it oil angles. quality oil anchors. So the oil anchors are alternatively known as roll pitch yaw anchors. Roll pitch yaw. Okay, roll axis. So this roll pitch yaw comes from the naval domain, the ships, and then aerospace field, particularly aerospace field, right? Rolling, pitching, and yawing moment, right? So we use it in robotics as well. That is one thing I want to tell you. The second thing I want to tell you is that when you describe your orientation using the three angles, right? There are so many different ways you can describe it. For example, you can tell, okay, I rotate around x-axis first, then y-axis, then z-axis. That is one way, one sequence. Or else you can say, I first rotate around x, then around z, then around y. That's yet another angle combination, right? Or else you can say, I first rotate around y, then x, then z. So it goes on like that. There are 12 different ways. And nobody can say which one is right, which one is wrong, because there's nothing wrong in any of these things. So this is something like assigning the positive and negative direction of a road. Let's say there's a road going in front of your house, right? Which is the positive direction, which is negative. There's no such thing. You are free to say, okay, let's say this side is positive, then of course automatically the other side is negative. Like that, conventions, right? Sign convention, you know that. So here also, out of these 12, you can pick up anything you want. Anything you want. But if you just make it free and everybody can use anything they want, even though mathematically correct, is a confusion in the field, right? So therefore, there should be some sort of convention that when we define roll pitch yaw or the three angles, we select one of these out of the 12, right? So usually, most books and the research papers that you refer to, they use ZYX, this one. I don't know why. Maybe it is right in the middle, right? Democratically selected. ZYX. Around Z axis, around Y axis, and then around X axis. So you get different angles, right? So Z axis is usually yaw. Then comes Y axis, it's pitch. X axis, roll. It's a yaw, pitch, roll kind of thing. But if you want to change this to a say different version, XYZ, you can do that in MATLAB, right? If you have the rotation matrix, right? If you have the rotation matrix, but just because you see the rotation matrix, you don't know what are these angles, right? So let me show you my MATLAB again. Can you see my screen?
Yes, sir.
Right. trying to get to this function. Give me a few seconds. Right. So this is a code I have written for something else, right? There I want you to pay your attention to this one. Look at this one. What is it? RPY angles, the roll pitch yaw angles. Roll pitch yaw angles, right? I want to calculate what is the angle around roll axis. That is, roll axis is usually x-axis. And what is the angle around pitch axis? Pitch axis is usually y-axis. If you look at a plane, the wings, right? That is the y-axis. So if you rotate the plane around the wings, right? Wing axis, pitching up and down, right? So when you climb up, it's a positive pitch. When you land a plane, it's a negative pitch, right? You are coming down. Or sometimes you don't change the pitch angle when you come down. You slow it down so that it naturally comes down because the lift is low, right? The fighters and other very agile planes, they actually have negative pitches, not the passenger ones, right? So this is additional information. Then the MATLAB command I'm using is this one. So if you look at it very carefully, you will see ROT-M, that is rotation matrix. Then number 2, rotation matrix 2, EUL, oil angles. Now, if you remember the matrices that we dealt with, 3x3 matrix, that is a rotation matrix. If you see the rotation matrix, right? For example, what is that? Say ROT-X. I give some figure value, right? Pi by 12 or whatever, right? You get this matrix. Now, let's say you have no idea about this angle, pi by 12, right? Because I typed it, you know it. But otherwise, if you just see the rotation matrix, this one, you have no idea what this rotation is. Okay, around which axis, what angle, you have no idea. So, if you have the rotation matrix and you want to find out what are the 3 angles around x, y, and z, right? MATLAB provides this command, ROTAM to EUL, rotation matrix to oil angles, right? Then you have these arguments R06. Don't worry about that. This is a matrix. And then after that, I have this within the inverted commas X, Y, Z. So I asked MATLAB, I want in this configuration, X, Y, Z configuration, not Z, Y, X or any other. Okay. Because you know the same orientation, you can achieve the same orientation going through different rotation sequences. You don't have to go through XYZ all the time, or ZYX, or whatever it is. You have to ask MATLAB which is the configuration you want the angles in, right? And after that, I have put here to convert radians to angles, right? So that we can see it easily. So, so if I run this program, right, you can see RPY angles are generated like this. The first angle, which is around x-axis, is 148 minus and around y-axis, the second one, right, is like 40 degrees and then minus 10 degrees. Okay, so this is how you convert a rotation matrix, or rather calculate the RPY angles, rho PTO angles from a rotation matrix. Any question up to that point? Is that clear to you? The three angles and the rotation matrix. If you know the three angles, you can calculate the rotation matrix. Of course, you can do that. And if you know the rotation matrix, you can calculate the three angles also. Right. Now, we have a choice here. Either we want to stick to oil angles or fixed angles. And out of these 12 options, right, optional sequences, we will pick up ZYX, okay? So then let's look at oil angle rotation. So here you can see the first rotation, right? First rotation is around Z axis because we have selected the sixth one on the list, right? Sixth one on the list, which is this one, ZYX. So we rotate around Z axis by an angle alpha. So what is the rotation matrix for that? After the rotation, we give a name to the matrix, the coordinate frame, right? It is B dash. It is B dash. After this rotation, the coordinate frame is B dash. So therefore, the rotation matrix is AB dash R. AB dash R. So B dash with respect to A. And we know that it's a rotation around Z axis, Z alpha, or Z alpha. And after that, a second rotation comes in. And this time we rotate around what? Around y-axis, okay? Because ZYX is the sequence. So y-axis. Now it is not the previous y, but the new y, YB dash. Okay, YB dash, the red one. Now you rotate around that axis by an angle beta, and the new coordinate frame, this is the green one now, right? Is called YB, is called B double dash. B dash goes to B double dash. So the rotation matrix between these two frames is B dash to B double dash R. B dash to B double dash R. And then you rotate B double dash around its own x-axis. So which is X B double dash, this one, right? By an angle gamma. So when you do that, you reach the final orientation of frame B, final orientation. So we'll give it a name B, final orientation of frame B, right, is B. So therefore, this final rotation is B double dash B R. So how B is disoriented with respect to B double dash. Okay. So now between A and B, there are two intermediate coordinate frames now. Between A and B, there are two intermediate coordinate frames. One is B dash, the other one is B double dash. Now, as you saw earlier, you can apply the chain rule here, right? You are working from one coordinate frame to the next one, to the next one, to the next one, and so on, right? According to the chain rule, you can write it like that. AB dash R times B dash B double dash R times B double dash B R. then these guys cancel out. What remains is A, B, R. How B is oriented with respect to A. Very easy and straightforward. After that, what you do is you substitute for AB dash R. So AB dash R is a rotation around Z axis by an angle alpha. So we call it RZ alpha. RZ alpha. Okay. And then you have B dash B double dash R. So B dash is here, B double dash is here. This is a rotation around Y axis by an angle beta. So it is RY, or rot Y, rotation around Y by an angle beta, followed by the final rotation around X axis, that is Rx, by an angle gamma. Okay, so when you do that, you get the total or final rotation matrix of B with respect to A. Okay, so again, if you go to MATLAB, I should have kept it open. You can exercise all these things pretty easily. So you can write down, say, rot X. The first one is rot Z. Okay, say some angle pi by 6, right? So let's say this is RZ, rotation around Z axis. Okay, let's give it a name. It's a rotation around Z axis by an angle pi over 6. So this is the result. And then the second rotation is around Y, right? It's a rot Y. Let's give it a whatever angle. So this is the second rotation matrix. And then give it the last rotation, Rx. This time it is rot X, right? To give it a negative angle, like 3. It's a big angle, negative direction, like that. So once you have all these 3 angles, if you want to find out ABR, so I can say ABR or ARB, whatever way you want to call it, right? That is the rotation matrix of B with respect to A. All what you need to do is you multiply RZ, then RY, then Rx. So this is the result you get. Okay. So it's pretty easy to work in MATLAB. So that's why I asked you, I will send you information, you download MATLAB and try it out, everything every day, right? So a little bit. So it's extremely important that you learn the theory, you learn the techniques, the mathematical tools, and in the same time, without any delay, you go to MATLAB, write a little code and see it for yourself. Okay. And in the final exam also, it's open book, and you're asked to use your laptop, right, and code it and write the code on your answer script. MATLAB based assessment is there in the exam, final exam also. Any questions? All right. So if there are no questions, I think it's time to get a break. Let's get a break and I'll see you in about 10-15 minutes. All right.
Excuse me, sir.
Sorry, I was muted, right? Yeah, so this is the oil angle rotation in ZY X sequence. If you want to do it in a different sequence, you are free to do that. But you have to keep that in mind. What was the sequence, right? You rotated angles around which axis? First axis, second, third, and so on, right? Even if you go beyond that, that's also okay, right? Mathematically speaking, it's very generic. But when you apply it for robotics or any other autonomous vehicle, usually you don't go beyond 3 axes, right? Now, you can try to explain the same thing we just saw a more elaborate way like this. If there's a vector belongs to B, so we'll call it BP. How do you write this vector with respect to B dash, the immediate preceding vector coordinate frame, B dash B? So what you do is you pre-multiply the vector with B double dash B. Okay, so this will rewrite the vector, right, or change the description of the vector VP, right, so that it is now referred to B double dash. And now how do you write B double dash B with respect to B dash B? Right, you write it this way by pre-multiplying B double dash B with B dash to B double dash R. So always you are writing, you're multiplying this vector with rotation matrix in front of that. Then you change the reference coordinate frame. And then you eventually write it with respect to A. Now the vector you have is B dash B. It's like this. Okay. So now in the final equation here, if you replace B dash B with this one, and then B double dash B with this one, you get this one. Right? So AB dash R, B dash B double dash R, B double dash B R. So this is the rotation matrix of B with respect to A. So like that. So same thing we described yet another way. Now, if you want to rotate the frame around the fixed axis, fixed means the blue frame, okay? Fixed means the blue frame, right? So now the roll PTO are with respect to the blue frame, right? And you can find out slightly different mechanism here. So first rotation is around, let's say this time we reverse the sequence, right? X, Y, Z. For a purpose, I'm doing that, right? You will see a bit later why I reverse the order, right? Now this time X, Y, Z, and it is fixed angles. Earlier it was Z, Y, X, and was oil angles. Now the first rotation is around the fixed axis X, fixed axis X, this one, by an angle gamma. So angle around that axis remains the same. The earlier also, the angle you rotated around x-axis was gamma, and this time also it's gamma, right? So let's focus on the first rotation. After the first rotation, right, a vector which belongs to the rotating frame, right? Let's say it is BP. After the rotation, you write it like Rx gamma BP. Straightforward, right? The rotation matrix is Rx gamma. First rotation is around x-axis. So now the vector is AP, right? Then you have the second rotation. So the second rotation is around y-axis, around y-axis, the blue y-axis. Now, because it is with respect to blue y, right? You don't have two coordinate frames to relate it to. It's the same coordinate frame because the axis is the same. So it's just a rotation, ry, this time around y-axis by beta. And the vector that you rotate is AP. This one, not this one, right? So bring AP over here. And then you can substitute for AP, Rx gamma BP, Rx gamma BP. This is the reverse order, right? Around X first, around Y second. And now the vector description is AP. The vector description is now AP, is given by this. And after that, you have your third rotation, this time around Z-axis by angle alpha. You have a vector AP, you rotate it by around Z-axis by an angle alpha. So you pre-multiply it with RZ alpha. It's a vector operator, right? Then you substitute for AP. AP is equal to Ry beta Rx gamma BP. So you get this one. So this is after third rotation. Now, what you have on the left-hand side is AP. What you have on the right-hand side corner is extreme end is BP. And in between, right, we have the rotation matrix of B with respect to A. Okay. Now, if you look at that one, it is RZ alpha, Ry beta, Rx gamma, right? There you can see the first rotation over here, second rotation over here, third rotation over here. On the left is the last rotation. On the right is the first rotation. Okay. And if you look at the expression you got earlier, you had the first rotation on the left, second rotation in the middle, and the third rotation on the right. So the rotations are going from left to right. If it is oil angles, if it is fixed angles, they are going from right to left, completely opposite order. All right. Any questions? Right, fine. Now, we have a question. In engineering, in robotics, which one of these two actually makes sense? Fixed angle or oil angles? The answer is oil angles. If you look at engineering apparatus like a robot arm, it has the base, link 1, link 2, link 3, and so on. So when, say, link 5 rotates, it rotates with respect to link 4, the preceding link, right? And if you look at link 4, when it rotates with respect to link 3, this preceding link, right? Say link 5 does not rotate with respect to link 0, right? Because 0 is not the reference frame for link 5. 0 is the reference frame for link 1. And link 1 is the reference frame for link 2. And link 2 is the reference frame for link 3. It goes like that, no? So therefore, we don't have fixed angle rotation in robotics. So it's oil angle rotation, right? Keep that in mind. So in oil angle robotics, oil angle rotations, or in robotics, we always rotate, multiply vector rotation matrices from left to right. First rotation, second, third, like that, okay? Now, so we continue the discussion using oil angles. So if you have three rotations, first one around Z axis by an angle alpha, second one around Y axis, angle beta, third one is around X axis, angle gamma, right? For a complete orientation representation using three angles, this is the matrix you get: R Z alpha, R Y beta, R X gamma. And you know, these are basic rotation matrices. These are all basic rotation matrices. So that's why I asked you last week to derive it yourself. Had you spent that half an hour and derived the rotation matrices, you would have been in a much better position to understand these matrices, because you would have seen them yourself. And then it looks like something familiar to you on the screen. So it's easy for you to understand. Because you didn't have that little time, you see it as a new thing, alien thing. So it's not very familiar to you. So the first one, R Z alpha, like this. Second one, RY beta, like this. Third one, RX gamma is like this. Now you multiply them together, right? You multiply them together. So please do this exercise, right? You have the answer here. But you multiply these two matrices first and get the result, and then multiply with this one, right? As a homework, please do that, and you will get this matrix. So this is the orientation representation matrix, one single matrix which will represent the orientation of a frame with respect to another frame. So this can be an aircraft, this can be a ship, a vehicle, this can be a robot, can be anything. Using three angles, oil angles, alpha, beta, gamma, around Z, Y, and X axis. One single 3x3 matrix. Please do that, okay? And also use MATLAB and give some angles and figure it out for yourself. So this matrix is what is seen by most of the flight controllers in airplanes and other vehicles, and check for itself whether the alignment is okay, the orientation is all right, okay?
Excuse me, sir.
Yes.
There are C and S. Is that stand for cosine and sine?
Oh, yes. Yes. C for cos, S for sine, right? Okay. So then the inverse problem. The inverse problem. You already saw the inverse problem in MATLAB, remember? Euler, the rotation matrix to Euler transformation. We gave the rotation matrix and got the angles calculated. Remember? Three angles. So this is what is happening inside MATLAB when you type that command. You have the rotation matrix, ABR, like that. And now you know the analytical description of that matrix using alpha, beta, gamma. There are three angles in that matrix. Three angles. You have three rows or three columns. Using these numbers, 9 elements, you can calculate alpha, beta, and gamma. It's not that difficult. If you get the rotation matrix, you can do this inverse calculation and calculate what is the three angles, how much this has rotated around z-axis, how much around y-axis, and how much around x-axis. You can calculate these three angles. You have to stick to the order, right? First one around z, first, second y, third x, because this matrix has been derived for that order. If the order is different, it's a different matrix, okay? Right. So then this is simple mathematics. You can follow it yourself. You have R1, 1, 2, R3, 3, the 9 elements. Okay. So if you look at this one on the right hand side, if you want to find out cos beta, right? What is cos beta? R11 square plus R21 square. So is that right? R11 and R21. These are the two elements in the first column. Two elements in the first column. This one. Is that right? Cos alpha, cos beta, get the square. Sin alpha, cos beta, get the square. Add them together. Is that cos alpha? Sorry, cos beta? Yes, it is, because the square here is cos square alpha. And then square here is sin square alpha. When you add them together, it's 1. So cos beta. So cos beta is square of, get the squares of these two numbers, add them together and get the square root. And that is cos beta. Sin beta, where can you find sin beta? 3, 1. Where is 3, 1? 3, 1 is over here. And it is minus sin beta. So get the minus over here. And that is sin beta. So how can I find beta then? When I have cos beta and sin beta, you get the ratio, and that is tan beta. You can calculate beta. But getting simply the ratio is not the right thing, because you know you have 360 degree, right? 4 quadrant angle. You know exactly where the angle is. Like for example, when it is in the 3rd quadrant, you might get the same angle in the 4th quadrant, right? Or 2nd quadrant and the 3rd quadrant. So you need to see which quadrant you are in. Therefore, the cosine and sine, when they come, you need to know their signs, right? That is why when you do the arctangent calculation or tan inverse calculation in MATLAB, you need to use atan2 command. This is the 2 argument arctangent function in MATLAB. You give the sine beta, that is minus R31, comma, and the cosine of that angle, square root of R11 plus R21 square. Then you can calculate beta. Okay, so same way you can follow through, right, to calculate alpha and gamma. So that is the inverse process to calculate angles from the rotation matrix. Now, what if the cos beta is 0? If cos beta is 0, beta is plus or minus 90 degrees, right? In that case, this doesn't work. Cos beta is 0 means you can't divide by 0. So you are in a situation called mathematical singularity. Mathematical singularity. So it is not only a mathematical problem, it is also a physical problem. In that situation, how do you control the robot arm, right? How do you control the robot arm? Of course, not every mathematical problem is a physical problem, right? Mathematical problems are sometimes because of the way you define, way you model the physical world. There are so many different ways of modeling the physical world. So just because there's a mathematical singularity doesn't mean that you necessarily have a physical problem, right? unless you stick to this mathematical model for controls. So if you use this mathematical model to control a robot arm in a singularity, you have this problem, mathematical problem. So you need to figure out a different way to represent orientation if you undergo beta 90-degree situation. So this is beta is, what is beta? If you look at beta, beta is the rotation angle around y-axis, right? Around y-axis. So if you are a pilot flying an airplane, right? Your y-axis is your hands. You stretch your arms horizontally. This is your y-axis, the wings. And you rotate 90 degrees around that axis. So you are looking up, climbing up 90 degrees. Or the other way around, you're climbing down 90 degrees. So these are awkward positions anyway, right? You don't fly like that. And mathematically also is a tough configuration. It's a singularity. So that, but in the usual flying, you don't encounter that situation. Okay. So in that particular singularity, beta equals 90 degrees, cos beta is 0, sin beta is 1. Right? So then if you look at your rotation matrix, which is this one, you have cos beta, you have sin beta, right? Cos beta is 0, sin beta is 1. Likewise, you can replace all betas here and you get this equation. So this matrix. So the rotation matrix when beta is 90 degrees is like this. And this is the illustration here when beta is 90 degrees, right? So see whether you can track that down. The first rotation is around z-axis by angle alpha. So once you do that, you get this orientation, right? So, and after that, you rotate around y-axis. So after the first rotation is the blue frame, right? Sorry, red frame. And the second rotation is 90 degrees. So you are rotating around this axis by 90 degrees. Then what happens? This Z axis falls on the horizontal line, and this axis aligns with the x-axis aligns with the former z-axis. This is the problem. Can you see that point? So this x-axis, it rotated to this point, okay, after the first rotation, and after the second rotation, it goes down vertically, aligns with former z-axis. So when you align your axis with a different former axis, like Z, Y, or whatever, you are in a singularity. You are in a singularity. So this happens when you have a seriously big, like 90-degree angle turns, right? And this is the rotation matrix. If you see this very carefully, you can figure out in these four elements, we have the angles, and it appears always as alpha minus gamma, alpha minus gamma, alpha minus gamma, alpha minus gamma. We know beta is 90 degrees, right? We want to find out alpha and gamma. But the problem is now in the matrix, we don't have alpha and gamma separately. Okay, now if you look at the previous one, they were separate. Alpha, gamma, you can find out cos gamma, cos alpha, like that, separately in isolation. But when beta is 90 degrees, it's not so. When beta is 90 degrees, it becomes like this. Now alpha and gamma are not isolated. They are together always, alpha minus gamma. So if you continue your mathematics, the inverse problem, you can find alpha minus gamma, but you cannot find alpha or gamma separate. So therefore, it doesn't work. Do you understand the point? We cannot continue the inverse problem when beta is 90 degrees. And we call it a singularity. You cannot calculate alpha, you cannot calculate gamma separately. But you can calculate alpha minus gamma, the difference between alpha and gamma. Now, if this angle is minus 90 degrees, right, situation is different. Then you get your rotation matrix like this. Now you have alpha plus gamma, alpha plus gamma. You can calculate alpha plus gamma, but you can't say what is alpha, what is gamma differently, right? Say alpha plus gamma 50, you don't know how much of that 50 is alpha and the remaining part is gamma, right? So this is the problem. So this is an illustration about the singularity problem, right? What you see here is the World War I vintage biplane, and there's a pilot in the plane, right, who is driving the plane. And then you have the gunner here, the rear gunner. Gun is mounted on this rig here, and it is a 2 degree of freedom mechanism. You can rotate it around you like in azimuth, and then you can control the elevation, azimuth and elevation. Okay, so using azimuth and elevation, you point the enemy plane and try to shoot it. That's how you do, right? So the question here is, in which of the two elevations? Now this is the elevation angle. This is the elevation angle. Okay. So this is the enemy plane. So if the enemy plane is up here, elevation angle is high. If the enemy plane is over here, elevation angle is low, like that. Okay. So in which of the two elevations, 25 degrees and 80 degrees, is targeting the enemy plane easier? So if you are the rear gunner and you want to shoot down the enemy plane, and which angle would you prefer, 25 degrees or 80 degrees? Any answers? No answers? There is an answer in the chat room, 25 degrees. Vigitharan. Any other answers? Which angle, which of these two angles, 25 or 80, right, would you prefer as the gunner? You are the gunner, right? You want to shut down the plane. If it comes 25 degree elevation or 80 degree elevation. Right. I think 25 is correct because 25 is a nice angle. The gunner can point the gun and lock it to the target easily. But whereas if it comes like 80 degrees, then you are looking at probably this direction, right? Like that, right? Then some people think that it's difficult for the gunner because he has to look up. It's not the case, because even if you have fully automated gun, there's no human gunner, right? It's automated. Still, you have this mathematical problem. This 90 degree problem. Okay. This is like beta, angle beta, getting closer to 90 degrees. 90 is tough. 80 is closer to tough. Okay. It's not easy. Why? Because you know it's difficult to calculate the other two angles in one way. On the other hand, if you continue to the next guiding question, you will understand it in full. What about the targeting capability of the mechanism when the enemy plane is at 90-degree elevation, exactly 90-degree elevation, right? How many effective degrees of freedoms are there at 90-degree elevation? So this mechanism is a 2-degree of freedom mechanism because you have two angles, right? This one axis, this is the other axis. So by controlling the azimuth and elevation, you can target almost anything in the air, right? In the space, almost anything. Because you have two different axes. They are normal to each other. So generally speaking, this is like say XY table. Using XY table, you can reach to any XY position easily, right? Now this time we don't have X and Y, but we have two angles, azimuth and elevation. But the problem is when the elevation is exactly 90 degrees, right? You are losing your 2-degree of freedom capability. Your 2-degree of freedom capability, because in any other elevation, let's say this elevation, this is pretty much like 30 degrees, right? Or 25. Now, when you rotate your azimuth, right, you can track the vehicle by controlling the azimuth. You change your azimuth, and even if you keep the elevation same or slightly adjust elevation also, you have 2 degrees of freedom, right? You have the complete use of 2 degrees of freedom. But when the elevation is 90 degrees, right, around 90 degrees, you can change the elevation and get some motion. But if you control the azimuth, it's not going to help. In any of the azimuth angles, the gun will be pointing upwards. Azimuth has no effect on the pointing direction when the elevation is 90 degrees. So you can imagine that at 90-degree elevation, it looks like you have lost your azimuth control. There's no use of azimuth. Because even though you control your azimuth, nothing happens to the direction where the gun is pointed at. Losing one or few degrees of freedom is the result, right, if you are in a singular configuration. So we call we say it like this: a mechanism is said to be locally degenerated, meaning that you're losing degrees of freedom when it behaves as if it has lost one or more degrees of freedoms, which could happen at some orientations known as singularities, right? So that's the complete description of mathematical singularities. Okay. Now, this mathematical singularity is a mathematical modeling problem, right? As I said earlier, it doesn't mean that physically you can't do that, right? Certain mechanisms, they have inherent singularity. Of course, that is a physical thing. Then, of course, there's no way out. All right. So that is why you may have seen the old Air Force movies and all, where the pilots are trained And sometimes they say, okay, during the training, they are trained to stay right above the enemy planes, because when you are right above the enemy plane, you have a pretty good chance of escaping, right? Not getting shot. But of course, during the time when the gunners were there, rear gunners in the azimuth elevation rig, right? Not anymore. So, but anyway, even nowadays, there are relative positions for the aircraft to stay in order to have increase the chances of survival. Okay, so it's all about these singularities. Now, if you can get rid of the singularity, if it is it's just a mathematical problem, right? You can think about the other ways of representing the orientation. One is Euler parameters. Euler parameters, right? Not Euler angles, but Euler parameters. So what are Euler parameters? Euler parameters are actually 4 parameters. We give it a name: epsilon 1, epsilon 2, epsilon 3, and epsilon 4. 4 Euler parameters. And this is how we define them. First Euler parameter, epsilon 1, is Wx sine theta by 2. Second one, Wy sine theta by 2. Third one, Wz sine theta by 2. Fourth one is cos theta by 2. So if you look at this right-hand side, right, what you see is Wx, Wy, Wz. So this is like x, y, z coordinates, right, of a certain point. This point, it is the vector W. Vector W. This is a unit vector, one unit. It has 3 components: Wx, Wy, Wz. Okay, this one as Wx, Wy, Wz. It's a unit vector. So this is the axis of rotation, actually. Axis of rotation. So if you look at these 2 coordinate frames, blue and red, right? Let me pedal back. This one, right? Or any other one. Say any configuration, this one or this one, or whatever. When you have the final orientation and the initial orientation, right? A and B. When you are given the 2 coordinate frames, you can describe how the second coordinate frame, the relative frame, has rotated around the first coordinate frame by a certain angle without going through 3 rotations, x, y, z, o, z, y, x, or whatever. You can say there is an axis of rotation, there is an angle of rotation. To orient the relative frame to its present orientation, starting with the reference orientation of the reference frame. Okay, just one rotation around a certain axis. So that is what is called the axis of rotation and then the angle of rotation. So you can actually relate any 2 coordinate frames using Euler parameters like that, right? Euler parameters, they have Wx, Wy, Wz, 3 components of the unit vector, and then the angle of rotation, that is theta. Now, if you find out Wx, W1, Wz, you know the axis of rotation. And then if you know theta, that is the angle of rotation. So you can easily represent your orientation using Euler parameters. And you have the normality condition W is 1, the unit, because it's a unit vector, right? So all 4 of them, the 4 element parameter, Wx, W1, Wz, we have to have W, sorry, epsilon 1, 2, 3, 4. So these are the Euler 4 Euler parameters, and they are added to 1. So if you do it here, Wx, W1, Wz, and cos theta by 2, right? Get the square of here, square here, square here, square here. What you get? Wx square plus Wy square plus Wz square times sine square theta plus cos square theta, right? Then, because Wx, Wy, Wz is anyway 1, the unit vector, it is sine square plus cos square, which is also 1. Okay. So that is the declaration of the rotation axis and the angle and how the Euler parameters are defined. So there is a nice relationship between the Euler angles and Euler parameters, right? So let us do this very simple exercise. You can take a piece of paper, right, and sketch this one, the blue frame and the red frame. Blue frame is the reference and red frame is the relative. And this is a rotation around x-axis by 60 degrees, right? So if you go to MATLAB and type it in, rot x by 60 degrees, you will get this one, right? This Euler angles, right? And we call it direction cosine representation, DCM, direction cosine matrix, okay? DCM. Now, I want you to calculate the Euler parameters for this one, right? So, if you look at the Euler parameter representation, it says axis of rotation and angle of rotation. So, this time the axis of rotation is x-axis. So, what is the unit vector along x-axis? Because x-axis is the axis of rotation. It is 1, 0, 0, and that is W. That is W. And what is the angle of rotation? 60 degrees. Theta is 60. Okay. So once you know the axis of rotation and the angle of rotation, you can calculate the 4 Euler parameters. First one is Wx sine theta by 2. So this is Wx, that is 1. Sine theta by 2 means sine 30. Second one, epsilon 2, Wy sine theta by 2. Wy is 0. Don't worry about that. The third Euler parameter is Wz sine theta by 2. It is also 0. Then epsilon 4 is cos theta by 2. That is cos 30. Okay. So B with respect to A, the orientation, if you represent using Euler parameters, it is 0.500, 0.87. So it tells us, no? It tells us axis and angle of rotation, right? Now, if you want to find out the relationship between Euler angles and Euler parameters, it is over here. If you have alpha, beta, gamma for a particular orientation, right? If you have the alpha, beta, gamma angles, you can also calculate epsilon 1, 2, 3, and 4. And using epsilon 1, 2, 3, and 4, you can calculate the axis of rotation and angle of rotation. So they are related to each other. Now, let's look at the inverse problem, right? Because why we first thought of Euler parameters is because there is an inverse problem in Euler angles. When beta is 90 degrees, the mathematics fail. But you know for sure, there should be a way for an aircraft to fly vertically upwards, right? You have seen planes flying like that, right? Toy planes, not the actual ones, right? And also planes coming vertically down, head down, right? That's a possible maneuver. It's not impossible, it's possible. What is not possible is to use the mathematics in that configuration. Plane can fly, right? If it has an engine, when you fly, you should be able to fly even upwards, vertically up, like rocket, right? There shouldn't be any physical problem, physical barrier. The problem is the way we model the mathematics doesn't allow you to handle that situation because of mathematical problem, right? And also, I have to tell you, I think earlier also I told you, there are some mechanisms like the elevation azimuth 2 degree of freedom mechanism. It's not a mathematical singularity, it's a physical problem, okay? Now, let's say if you know the ABR, the rotation matrix, and you want to find out the epsilons, right? So once you substitute for the rotation matrix, which is here, 3 by 3 matrix, right? Using Euler parameters, you get this one. Right? Without a proof, I'm just showing it to you because our discussion is on towards robotics, not going deep down into Euler parameter mathematics. So this is the rotation matrix in terms of Euler parameters. And on the left-hand side is the rotation matrix. Now, our problem is, given the rotation matrix, how can we calculate the epsilons? Again, you can look at the nature of the elements here on the right-hand side, and then try to figure out some relationships. For example, if you add R11, R22, R33, the diagonal actually, right? The diagonal like this, it will be like 3 minus 4 times epsilon 1 square, 2 square, 3 square. And on the left-hand side, these are known. On the right-hand side, if you add these three Euler parameters, right, this is equal to 1 minus epsilon 4 square, because you know there is this equivalence, right? This one. Epsilon 1 square plus 2 square, 3 square, 4 square is equal to 1. If you get any three of them squares added together, it's equal to 1 minus the square root of the other one. So then you replace epsilon 1, 2, 3 from the equation, but bring in epsilon 4. So it's only one variable unknown in the equation. You should be able to calculate epsilon 4. And this is how you do that. So you can code this very easily into any software and calculate epsilon 4. So once you calculate epsilon 4, you have to calculate epsilon 1, 2, and 3. For that, you can find out equations like this. R32 minus R23 divided by 4 epsilon 4. And epsilon 2, 3 are also like that. There are equations you can write down to calculate 4 Euler parameters. But the problem is, if epsilon 4 is 0, if epsilon 4 is 0, again you are in the same problem. You can't divide by 0. You're stuck. But the beauty of this Euler parameter case is that as a lemma to get out of the problem. This is a serious mathematical treatment. You may have seen in the Euler angle case, it is three angles, alpha, beta, gamma, which means like 3 dimension. But when you get on to Euler parameters, it is epsilon 1, 2, 3, and 4. It's a 4-dimensional problem. So this is a typical mathematical approach. When you have a problem in 2 dimension, you bring it to another dimension, like 2 to 3, or 3 to 4, or 4 to 5, like that. Some of the problems in certain dimensions, you cannot solve in that dimension. You have to bring it to a higher dimension and solve it. Then you can bring it down if you want, right? So this is a 4-dimensional problem. So if epsilon 4 is 0, you can always figure out another set of equations. Because of this lemma says, for all rotations, any rotation around any axis, any angle, right? One of the Euler parameters is greater than or equal to half. So that's a lemma. For any rotation, all rotations, right? One of the Euler parameters is greater than or equal to half. So therefore, there's always one Euler parameter which is non-zero. Now you saw in the previous case here, 2 Euler parameters, right, are zeros. And you saw one of these parameters greater than half, see, 0.87. You always have one parameter which is greater than half. So you can first calculate that parameter, right? All what you need is a non-zero one, but if you get the biggest one, right, you are assured, right? So you solve for epsilon 1, right, like this equation. This is different than the first one, right? And if it is non-zero, you calculate the other 3 parameters using these equations. If that is 0, right, you calculate epsilon 2. And if it is non-zero, calculate the other parameters using this one. If this is 0, you calculate epsilon 3. Likewise, the first parameter, right, can be any one of the 4, right? Epsilon 3, 1, 2, 4, whatever. If it is not 0, you go ahead and calculate the other parameters. If it is 0, you drop it, you stop it, and try to calculate another parameter. Okay? So therefore, there's always a way out for you to calculate Euler parameters. So I'm giving you this one as another homework. Don't have to submit to me, right? But do it yourself. Determine the 4 Euler parameters corresponding to the rotation matrix below. So you have rotation matrix. And also I can add to this one, why don't you calculate alpha, beta, gamma? The 3 Euler angles for this rotation matrix. What are the 3 angles embedded in this matrix? So this matrix represents orientation of a vehicle, right? And how do you know what are the angles? 3 angles. And also calculate the Euler parameters for this rotation, epsilon 1, 2, 3, and 4. Right? Quite a lot of information, quite a lot of knowledge around one matrix. Okay. Right. So that's about it for that lecture. Any questions? We have some time because time is not enough for me to start the next lecture. So I want to hear from you any questions, because it's pretty sure, right? You might not be able to understand the the whole thing. So you may have a lot of things that you don't understand. So you need to ask questions, okay, to get all these things that you don't know, right, to get it answered. So it's time for you. We have a few minutes. Please ask anything, any questions you may have.